Witam Państwa, and these are the only two words I'm going to say in Polish from this point on, without in English. And I know that at the very least, I'm not sure, at the very least, we have a native speaker of English. A student from Canada, whom I have in my class, Materials for Space. Welcome to everyone. And today, I'm going to talk about high-entropy alloys. I call them cutting-edge materials for space applications. And I'm immediately looking at Professor Pichur, because I don't know whether he would agree with this.
I agree for everything.
Why I'm saying this? To make things obvious. These materials have not found applications yet. A couple of niche applications in some parts of the spacecraft, but these are the materials of the future. Niche materials indeed, but very promising. On top of this, for me, as a material scientist, this is incredibly interesting class of material. Because, for example, when I teach students introduction to materials, I make some assumptions that are in every textbook in material science. There are some assumptions regarding, for example, fusion, mechanical properties that do not find reflection in high entropy alloys. In a sense, I wouldn't say that we're dealing here with the we're dealing here with application of our understanding of behavior of conventional materials. That's why, for me, in addition to the fact that these are potentially very important materials for future space applications, it's a fascinating group of materials for people who do deal with material science. Okay, with no further ado, let me go ahead. Remind those of you who were in my seminar last fall. Last fall, I talked about important classes of materials for space. I talked about refractory metals, ultra-high temperature ceramics, and carbon composites. Today, the fourth class of materials, I would like to share my understanding of high-entropy alloys. Whenever we have discussion on materials, particularly materials, load-bearing materials for structural applications, so structural materials. In the context of aerospace and strictly space applications, we always have to remind ourselves of the king of the field. These are so-called nickel-based superalloys. It is really a gold standard of aerospace, not just space, of aerospace materials, without which we wouldn't have jet engine. We wouldn't have, there is no other class of materials that could compete today in major applications for jet engines, for jet engines, for rocket engines. Actually, we wouldn't be in space, literally. The very well established class of materials, optimized over the last 4 decades, is a baseline for our consideration of materials that are needed, because even nickel-based alloys, superalloys. This is the only class of materials, alloys, that we call superalloys. So again, it's a baseline for the consideration. All other materials are being designed, have been designed, or are being designed with the demands in space. These are as I said, a summary of what I said, quintessential high temperature structural materials. They were designed a few decades ago, but they've been optimized since then. They've been designed with aerospace applications. They are multi-element alloys. We say nickel base, but the key is the use of a number of elements in small numbers, indeed, in small amounts, if you will. Why? Why nickel-based superalloys are so important, so successful in the applications in question today? Because all other materials, alloys that we know, have temperature limitations. When you look at this meta plot of specific strengths, so strengths divided by density, as a function of temperature, absolute temperature in this case, you can see here aluminum alloy. The melting temperature of aluminum is 660 degrees C, so practically they cannot be used above 400 Kelvin. Titanium alloys extend this temperature limit, but they're far away of what we need. As a rule of thumb, number to remember, today we are talking about all these important properties at 1100 degrees C, so close to 1400 Kelvin. Authentic stainless steels extend the applicability of titanium alloys up to this point, and then superalloys kick in. But it's really superalloys, nickel-based superalloys in single crystalline form that this is this gold standard. Not just nickel-based superalloys, but single crystal superalloys. And you can see the temperature limit is around 1100 degrees C. Fortunately enough, it is what's needed in today's applications. But it's not enough. It's not going to be enough in the future. Just one slide. I mentioned 1100 degrees C. Nickel-based superalloys in their singly crystalline form offer you excellent behavior in elastic region, so material stiffness, in plastic, and now we are talking about plastic deformation, they're strong and ductile. That's the combination that we need for structural materials. They are also, the oxidation resistance is good, and they have particularly excellent creep resistance, which is of major concern. But also the fracture toughness is great, and fatigue resistance is good. So again, this is the starting point. This is what we need at 1100 degrees C. But last fall, I already talked about the three categories I listed at the beginning. Refractory metals, ultra-high temperature ceramics. These are the classes of materials that are either already helping or will be helping in the future. So that's kind of keep these properties. Keep in mind the temperature as an introduction to high entropy alloys. Now, looking at high entropy alloys, I will be talking about their composition, about atomic structure, but very briefly, I really will focus on core effects related to high entropy alloys. And I will point to differences between, let's call them conventional alloys and compositionally complex alloys, and high entropy alloys are compositionally complex. Typically, we don't talk about history of alloys, but I think it's in this case, because it's such a unique class of materials, and the way it was developed, for me, is fascinating. So let's start with this aspect, very briefly. Until I would say 2005, so practically, let's call it 20th century alloys, the well-established alloys we are using today successfully. What dominated was what we sometimes refer as a one-element paradigm. But altogether, materials designer, people responsible for material selection, linking their efforts to people, to material scientists, the bottom line, as far as alloy was concerned, was a simple rule that there is always one dominant element. For example, iron, nickel, aluminum, and the list goes on, and these 20 different elements. Then what you do, you start with a pure metal and add relatively small additions of other elements. Because an alloy, by definition, is a combination of basic element plus some other additional elements. Few examples: steels. Steels are alloys of iron and carbon, but of course there is tens of thousands of steels with very different chemical compositions. I mentioned nickel-based superalloys. They are based on nickel. The dominant elements. This is one element paradigm. Aluminum alloys, yet another example. And interestingly, I call it the unchallenged implicit assumption. I was at that time part of the game. I never really thought seriously about taking a few elements in nearly equal numbers. It's not that it wouldn't cross our minds, researchers in the field, but we knew it wouldn't work. No further considerations. Why? Because based on the experience we had, and we still have, when you add elements, very quickly you start reaching the point where the stability, let's say solid solution form, stability of the structure as we know, is sometimes for very good reason, sometimes it's a challenge, where inevitably, with a few exceptions, I may mention one of those later on, we produce brittle phases, they precipitate. So these are particles. And as long as strength is concerned, this is typically a plus. But adding brittle particles, intermetallic compounds, for example, such as nickel aluminum, titanium aluminum, very well-known classes. But this impacts ductility. And inevitably, the concern is the balance of strength and ductility. That's why pretty much no one talks about multi-element alloys, true multi-element alloys. Around 20 years ago, 22, 23, that's a bit of history. We saw a true revolution in alloy design, pretty much by chance. There were two scientists, one in the United Kingdom, the other one in Taiwan, the name mentioned here. I won't try to pronounce the Taiwanese scientist's name, but a British scientist by the name Kant. They actually started experiment in parallel. Then they joined forces. remember well, they started experimenting with multiple elements in near equal proportions. This was, in a sense, breakthrough approach. But the concept behind this, I call it a breakthrough concept, is that these alloys, from purely thermodynamical standpoint, have to have high mixing entropy. That we've known forever. That's nothing new. Simply the effort did not go in this direction to truly explore what providing materials with high entropy of mixing atoms really means. From the thermodynamic standpoint, that's pretty obvious. That's not surprising, but how it impacts materials' properties. So the concept was this increasing entropy of mixing. You know, the first approach is it probably should be a stabilizing factor for solid solutions that in most alloys are only when we add a few percent, for example, a few percent of copper into aluminum, or vice versa, copper, aluminum. Altogether, what we are going to talk about was a real challenge for what I personally call classical alloy design dogma. It didn't take long. Cantor developed what's today called Cantor alloy. It's an iconic alloy, if you will. Because whoever touches high entropy alloys, you know, that's the starting point. What he did, he took 5 metallic elements, cobalt, chromium, iron, manganese, and nickel, in practically equiatomic proportions, 20-20, 20-20. And that's kind of a nice illustration of how the structure of this alloy looks like. It's cubic, face center cubic, but it's based on a cube. You see 5 different colors from yellow to green to dark blue and so on. Atoms are distributed randomly, but because there is some pattern, if you will, because it's 20% of each. And very quickly, first mechanical studies prove that this Cantor alloy has a stable microstructure from temperature as low as liquid nitrogen temperature to 800, 900 degrees C. That was very interesting. Because not only, so there is no rapidly to ductile transition, really, actually they were looked at as very promising cryogenic alloy, not as much high temperature alloy. They weren't particularly, this alloy wasn't particularly strong, but it had exceptional combination of ductility and toughness. Again, especially at low temperature. So you could say, wow, there's wow factor, if you will. Very complex chemistry. Unusually complex chemistry, but very simple structure. But most importantly, you move from these temperatures and balance into the chemical composition, and you have again complex chemistry, but very simple structure, and the alloy provides quite a combination of mechanical properties, especially at low temperature. Again, no mention of space. This alloy wouldn't even be considered for a sec as a space material, because practically above 800 degree, 900 degree, we wouldn't have any use. for this particular high entropy alloy. Very quickly, around 2010, there was already, and that's the fascinating, pretty good understanding of core defects, core effects. Defects are one of them. 4 core effects. High entropy effect, lattice distortion, very slow, sluggish diffusion, and what people refer to as cocktail effects. So a combination of several factors impacting properties. Now, high entropy effect. The high entropy of mixing resulting from the presence of 5 major elements stabilizes what we call disordered solid solutions. I will show you an example in just a moment, with very simple crystal structure, equivalent to a single metal structure, all single metal structures or pure metal structures. By having elements with different atomic sizes, we have severe lattice distortions. There is an enhancement of strength, but at the same time, it slows down dislocation motion, which is responsible for plasticity, for ductility, sluggish diffusion. Because of different sizes, vacancies, or atoms, you can use it in parallel, the terminology, move much slower than in conventional alloys. And this is huge because creep, the mechanism that really is of biggest, if there is the biggest concern for high temperature applications, it is the creep resistance of the alloys. And the sluggish diffusion contributes to this. Cocktail effect. There are some first studies related to this effect, but the point is a contribution, it's kind of non-linear enhancement of properties. I mentioned the crystal structures. The simplest one, we have 14 Bravais lattices, metals crystallize in the simplest lattices from cubic body center, atoms at the corners, and 1 atom inside, face cubic, atoms at the corners, and atoms at the center of the faces, and thus in hexagonal. When you see the list of alloys, there is here like a dozen or so. These are the bases for practically all structural alloys in use. I'm not saying all, but practically all. They're all usually suspects when you look at the list of elements. Now, just 2 slides. Thermodynamics behind high entropy alloys. You have n components. In the Cantor alloys case, is 5. All of them have sometimes different, sometimes the same atomic fractions. You calculate the configurational entropy, finding the products of the 2 terms, summing them up from 1 to n, multiplying by the universal gas constant with the sign minus. In an equiatomics, for example, Cantor alloy, 20% of each element, xi equals 1 over n is 5. So 1/5. And you multiply, you get the entropy of mixing from this simple equation. Now, how does the number of elements impact entropy of mixing? By definition, in a pure metal, there is no entropy of mixing. We are not mixing atoms of the same substance. For 2, it increases to close to 6 in joules per mole times Kelvin, and it goes up. A typical high entropy alloy has entropy in the range of 10 to 20, let's say, but that's calculated based on the assumptions that the number is exactly the same. And this is what we are talking about. 5 elements, practically all. There are some 4-element high entropy alloys, but for practically all, we have 5 elements. This entropy of mixing is high enough to secure what we need, what we expect of high entropy alloys. Now, when you mix atoms, you kind of increase the random distribution, randomness of lattice points occupied by different alloys. That's where the entropy comes from. And altogether, I already mentioned it, under these circumstances, we produce very ductile, disordered solid solutions. That's the illustration. So you have red and just 2, in this case, red and black atoms. And in this case, is a disordered structure. So there is a random distribution of atoms in individual lattice points. Here you can see some order. This is actually, for 2 elements, intermetally compounds, yet another interesting class of materials, but I don't have time to talk. It was listed on my mega plot. I showed titanium aluminides, titanium aluminide. This is how the structure would look like, but they are ordered. And ordering, in the case of structural applications of the type we're talking about, is disadvantageous. Yeah, I just mentioned that nickel aluminum and titanium aluminum is not something we would be concerned about today. Now, going back to the free energy of mixing, look at this product. We have 2 ways of minimizing energy, which of course is an inevitable nature invention, if you will. You can do the following things to increase entropy, which minimizes energy. Either you increase the configurational delta S, or you increase temperature. Oops. And that's why the state of minimum energy leads to the stabilization of solid solutions without producing undesirable brittle phases. Going back to core effects, I mentioned entropy. I'm going to spend a few minutes talking about lattice distortions and diffusion. I will not address today cocktail effects. That's pretty esoteric. There's no good understanding of this. There is just an indication that sometimes the very presence of lattice distortion and diffusion leads to very strong lattice distortions. Sluggish diffusion leads to very interesting effects of no concern to us beyond this point. Lattice distortion. That's the simplest. That's a body center cubic structure in the presence of 1 type of atom. But here you see 5 types of atoms of different sizes. Immediately you see that the cube, the ideal cube, is completely distorted. And this is an idealization, because the distortions are really sometimes, because of the atomic size differences, even more so than here. What kind of impact it has on motion of dislocation, this line defect, that when it moves, when millions of dislocations move, a phenomenon of so-called slip takes place, leading to significant plastic deformation. There's, of course, oversimplification, but I can't spend any more time talking about this. And as a result, what we refer to as lattice, as energy landscape changes tremendously. Because if we have one element, essentially, and this dislocation moves, it follows a sine function. It kind of moves from one type of spaces to another in a way requiring very little energy. But that's not what we have here. And the local, each additional element, the presence of the dislocation in proximity to these elements leads to strong local fields, strain fields. Now, as a result, and that's something what's totally fascinating for me as a material scientist, someone who did a lot of studies on actually impact of dislocations on ductility, you name it. The line dislocation lines that are typically straight, or they have some edges, change. We call it the roughening of dislocation line. In most metals, so-called planar slip along well-defined crystallographic planes, minimizing these dislocations, motion energy is absent. In addition, a phenomenon, so again, for non-material scientists, I know it doesn't mean much, but I will mention it, that a phenomenon of cross slip kicks in, and as a result, dislocation path is very wavy. Now I warn you, what you are going to see has nothing to do with reality. But I just, preparing this lecture, I just took the liberty of challenging ChatGPT to model a dislocation line in a high entropy arc. A success is very appealing, if you will, so don't believe in this slide. Though it has some elements of truth. But I was kind of wondering, looking at the review papers, dealing with the activity of high entropy alloy review papers, I wasn't able to find a single illustration, not to mention high resolution electron microscopy imaging. No, we are not at this. That's incredibly complex. So again, kind of a lighter note, this kind of illustrates with so many mistakes that I won't even start. But imagine that this is a simple shape. It doesn't look like this, but it's kind of illustration. Now look at the dislocation line in high entropy alloy. Won't go. There's several mistakes. Again, I pushed GPT to apologize for these mistakes, but it didn't help much. Okay, but you can see, even this periodic energy landscape, that's in a single element. Dislocation moves and energy changes like this. But when dislocation moves in multi-element, high entropy alloy, you see what happens. Very different amplitudes, if you will. Frequency is different as well. The bottom line is, I don't know what value for you this figure has, but at the very least it says, look, everything we know in conventional alloys breaks apart in terms of the dislocation motion, breaks apart. We don't know how to, of course, people do it. It's a new area. What's the consequences of these lattice distortions? The dislocation motion is far more difficult And but we provide the stability of the solid solution structure. The solid solutions are strengthened. It leads to high yield and tensile strengths, but more importantly, as a prospective feature, is the retention of strength at high temperature, provided the compositional structure is probably properly selected. Why the strengthening is so pronounced? When you look at conventional alloys, black alloy, let's say you have an alloy made out of black atoms. How can you, one of the ways of making them stronger is using so-called interstitial atoms in between other atoms. That's why you call interstitial, but also substitutional atoms, which means that we are substituting an original atom with another one. And these substitutional atoms can be bigger or smaller. Now, that's pretty much it. And it's an important strengthening mechanism. But in compositionally complex alloys, we have a plethora of possibilities. Because we have 5 types of atoms. And the position of interstitial atoms, the size differences are far more pronounced. That's why, from this standpoint, I look at this and say it has to be much stronger. Now, slow diffusion, very quickly. Look at the so-called the equation describing how fast vacancies or atoms move through vacant sites. That's a classical equation. Whenever we teach diffusion, that's where we start with. D stands for diffusion coefficient, the material's property. T0 is a factor, different for different materials. Most important is the activation energy for diffusion, Q. Now, why in high entropy alloys, atomic diffusion is slowed down in a significant way? You look at this equation. In high entropy alloys, activation diffusion coefficient, activation energy for diffusion is much higher. If it is the case, the lower we have lower diffusion coefficients D, and it is the diffusion coefficient is essentially the material's property that controls how fast vacancies diffuse. It relates us to creep, again, probably the most challenging aspect of structural applications in space. I would say not probably, arguably. Physics, again, reduced behind this, vacancy mobility. Vacancies moving interact is a theoretical concept. Empty spaces don't move. Atoms move from one empty space in crystal lattice. But we tend to talk about vacancy as a construct. They interact with 5 different types of elements. And the very existence of different elements introduces strain fields, changes them and the distance between differing atoms. That's a complicating factor. And the migration is slow. And since diffusion proceeds through low energy pathways, these pathways are very complicated. Like a dislocation motion is becoming more complicated. All of this slows down diffusion. I probably should, again, This hasn't been proven yet, but there is a strong indication that a sacred number, vacancy concentration in single atomic alloys, that vacancy concentration is reduced, equilibrium concentration. What does it mean, or what would it mean? Because again, this is an active research area or calculation area. If we have less vacant sites, the diffusion slows down. It's kind of additional factor. Improved creep resistance in high entropy alloys is promising. Enhanced thermal stability. And even if additional phases ultimately emerge, they are created as a result of diffusing atoms. If diffusion is slowed down, the probability, inevitability, if you will, of diffusion is slowed down. And better radiation tolerance that potentially might have beneficial effects in space. Now, in the last, I told you about counteralloy. Since I would say around 2015 to 16, there has been further acceleration of research in these areas, and three major families of these ultra high entropy alloys emerged. Counteralloy is an example of phase center cubic alloy. I talked about it. So one category. Another is allowing for additional phases despite their detrimental effect. But really the third one of interest to us are refractory high entropy alloys with body center cubic structures. These are the alloys, because we use high melting point alloys, are of concern to us, talking about applicability in space. We already talked about interesting mechanical properties of several high entropy alloys, but by this category actually extends temperature range beyond what we have today, nickel-based superalloys. Looking at the periodic table, we are talking about these elements for refractory high temperature alloys. The most important are tungsten, tantalum, molybdenum, niobium, and increasingly titanium. Practically all, except for when I look one more time, I don't remember high entropy alloys with hafnium, but I do remember additions of the economy. So these elements, that's what we are talking about. Except for titanium, all of them have high melting points. Tungsten, 3,500 degrees C. Looking at these elements again, I am providing you with, sharing with you two most prominent ones at that point of time. One has four elements, in fact, niobium, molybdenum, tantalum, tungsten. Another one, that's probably the most popular one at this point of time, is, you see the elements, vanadium, niobium, molybdenum, tantalum, tungsten. Now, they already have proven in laboratory tests their ultra-high temperature strength and creep resistance. So their potential is there, but we face several challenges. Oxidation resistance. The fact that we are using heavy elements, tungsten is
Rhenium is comparable. Tungsten's density is practically 20 grams per cubic centimeter, the heaviest metal. So actually, density is high. As a result, specific strength is relatively low, strength per density, which has a huge impact on the weight of structures, parts, components that will be hopefully produced using high entropy alloys. Okay, I will skip this. Let's compare properties that we have available now, measured in laboratories of nickel-based superalloys, mostly properties measured in tension. Because of manufacturability, most of data you are able to find in literature are for compression, but more and more they are complemented by comparable properties in tension, so tensile properties. Look at 600 degrees C, you see pretty much the same, no big difference. Likewise, 800 degrees C, these are the ranges. The difference shows up when it comes to strength. WS stands for yield strength at 1000 degrees C. You look at the two ranges and you see a difference in the right-hand column. When you move to 1200 degrees C, it's for all practical purposes near or beyond practical limit for most nickel-based superalloys. And this is quite a respectable range. I want to tell students that this is not a scientific number, but what we call usable strength is around 400 megapascals. So you can see that high refractory alloys are fine. This is again practical limit. This is as close as it gets to the melting temperature of nickel, which is, if I remember well, something like 1440, something like this. Even at 1600 degrees C, there is already evidence of high strength in some high entropy alloys. So implications for space, kind of this crossover temperature when we are concerned about nickel-based superalloys is around 10,000 degrees C, and then the benefits are pretty obvious for still potential benefits. So refractory high entropy alloys outperform nickel-based superalloys as far as strength retention is concerned. This is actually another plot that nicely shows the differences between nickel-based superalloys. Inconel 718 is one of the best we have. You can see what happens. Strength goes down. It's in gigapascals, so this is 400 megapascals, and this is just 1213. Practically here, there is no further use, and you have 3 or 4 corresponding curves for different types of high entropy alloys. As far as creep is concerned, first and foremost, we don't know much about high entropy alloys. We don't have many research yet, but there is increasing amount of evidence that they perform very well. A summary of somewhat limited data is one, mechanisms change, but we do know that it's again limited to 1100 degrees C. And really, the first experimental proves that that the creep range for high entropy alloys is very promising. Above 1100 degrees C, up to 1600 degrees C. But I have to say at the same time, this is a developmental approach. We are not there yet. We hope this will be the case. As to say. Now, that's one of the first well-documented studies on the creep resistance of nickel-based superalloys versus refractory HEAs. The metric is 10 to minus 6 per second creep, which means every second material deforms by 1/100 of 1%. You have here data at 100 degrees C for nickel-based superalloys and up to 1400 degrees C. Even if the temperature is difference is so pronounced, look how much better refractory metals behave under this particular alloy. The lower the curve, the slower diffusion, the better creep resistance. Despite the fact that the temperature difference is so significant. We're talking 2 orders of magnitude, even 3, slower diffusion. So creep time, in practical terms, if the creep rupture time in a nickel-based alloy is a matter of months, in high entropy alloys, 2 orders of magnitude, we would be talking tens of years. Now, practical preferred materials for different types of application. Definitely, as far as, for example, in pumps, turbo pump rotors, discs, combustion chambers, hot gas structures, we don't need anything but nickel-based superalloy. But when we are dealing with nozzle throws, through which the gas escapes the engine area, the temperature are already, that's a huge problem these days, because the temperatures are above 1200 degrees C. This is where hopefully refractory materials with some protection because of the lack of oxidation resistance may kick in. They are strong candidates for some parts of thermal propulsion, nuclear thermal propulsion applications. It looks like in hypersonic structures, entry loads, this is where I understand that we have some niche applications as of today. So, kind of summarizing ultra-high temperature structural materials, refractory, HE components, and manufacturing, which, nickel-based superalloys, the manufacturing techniques are well developed. Nickel kind of lends itself to relatively easy manufacturability. As far as the most recent research right now, kind of alloying strategies is through adding light elements like aluminum or relatively light elements like chromium and actually producing a combination of high entropy alloys, PCC structures, I told you, plus what we call P2 microstructures. And P2 microstructures are typical of so-called intermetallic compounds. The issue is that though there are disadvantages of letting the other phase to be present, but there are also advantages. So alloy design is actually optimization, sometimes choosing from bad options, less bad option, if you will. Also, because of the oxidation, poor oxidation resistance, the strong area of focus is coating, and the usually suspect of additive manufacturing to manufacture future high entropy alloys. They've proven high potential, but I have to be very careful here and say they are still considered development material. But maybe because of this, it's so fascinating to watch the progress in this area. I use the same slide during my fall presentation, essentially saying that's the end of my presentation, but it's just the beginning of present and future challenges when it comes to materials used specifically and nearly uniquely for future space applications. That's what I prepared for you. Please, any questions, if you have to take a few minutes, so if you do have questions, I will be more than happy to try to answer or not to answer.
I'm talking material are currently in research for additive manufacturing. What are the problematics of possibility to produce it with additive manufacturing?
I am unable to answer the question, not because I didn't read about the topic. This is really very early stages. So I haven't found truly well-developed articles. But the chemical composition, complexity, dealing with 5 different atoms, will or does translate into some challenges.
Related about general manufacturing of those alloys. They are, I'm guessing, they are not really put into a furnace, and melted. Do they use like metal powders?
Metal powder, yeah.
Mixed.
Accretion. There was, I learned about actually, not knowing coming this time to our university, I learned actually about there is an article in the Department of the Materials Engineering, and one of the departments of Materials Engineering, they have an article where they actually produce powders of refractory, of refractory high entropy. So there is some research going on, very preliminary, HEAs University Club. And whatever I mentioned about a couple of niche applications, yes, it was through powder metallic composition.
Like when you want to produce a real steel billet, for example, like a bigger part, not really powder for coating, but a whole part.
Mm-hmm.
Like when you mix the powders and then melt them to achieve
The problem
chemical
is that
composition.
making is not impossible, but demanding
the melting temperature of most of these elements is at least niobium is 2500, but the major refractors, tungsten, tantalum, molybdenum is well over 2000 degrees C. Is it possible? Yes, but it will be very difficult. But not impossible. That's the progress you have. At this point of time,
I would like to ask you about melting point of these mixtures, because it's a huge problem in production of materials, because in some cases, we got the composite and alloy, because some of particles have a huge temperature of melting. So it's important to find the method of preparing of such alloy. So what about melting point of such mixtures? What was your opinion about possibilities of using the element with high temperature, like tungsten or difference, with high temperature of melting? What is your opinion of possibility of making the alloys with high entropy?
through melting, at this point of time, I don't see any way we could make 4 elements out of 5. I believe that we need to, plus most of these elements have already melting temperature about 3000 degrees C. But, I think out your question,
You know the difference?
yes. I'm just thinking out loud. I think that maybe you could use, you don't have to melt tungsten and other elements in the same furnace. So from the economic standpoint, in an extreme case, you would have 5 furnaces melting, and you would save a lot of energy. You pour everything, so everything will be molten at different temperatures. And to quenching or cooling down, it's speculation.
Okay, I know. Because it's also additional effect of evaporation of just melted metals with low temperature, with low melting point, and we must wait for elements with high melting point. So during this time is evaporation of melted metal.
Yeah.
So it's a huge problem
Sure.
in production.
With tantalum iron, I told you about, not an issue because we're dealing with elements with melting temperatures 13, 1400 degrees C, kind of iron, nickel, copper range. And that's not a big deal. Casting is not a big deal. Cast irons are produced entirely through melting.
So we will see what will be future.
Absolutely. But I think that in the university environment we should be open for materials who are not being applied yet. That's actually our role. And I'm not necessarily saying you are experimenting with new materials that are not quite there yet. And for me, as a researcher for so many years, I'm not only excited to do new things, kind of minuscule changes at the edges, kind of slight refinement was a big deal.
Just like a comment, I think we not only need to melt all the elements, so we can produce quite good high-entropy materials, by in this case, just filtering powder, longer time, in temperature much lower than melting point of that. Therefore, I can produce counter-alloy. Just filtering is quite below 1000 degrees for several.
Okay, I know, but sometimes it's a problem, and the question is, it is alloy or it is composite?
In such a case, I thought quite good alloy.
Homogeneous structure.
Very homogeneous structure. The problem is, geometrical problem is that since you are not melting the element, you are still have a hole. It depends on the pressure you are using, but there are many factors.
What is the size?
Rays are quite big. Much. I played with iron, cobalt, gold, nickel, and aluminum, and the grade of the alloy phase in such a way was some 20-40 times higher than the grade of phase from asphalt.
Also really big grain size.
Very good.
By the way, when I was talking about powder metallurgy, I said kind of a cluster of areas, but of course,
Additional method of producing the only, for example, we would like to melt molybdenum with zinc, which evaporates immediately at a very low melting temperature, but if it is floated in the capsule and make long stay in it, we will get quite detailed.
We have questions from chat. AI or CR additions would provide protective scale, which however degrade at so high temperatures. Do you think that reactive elements IFE applied commonly at lower will be helpful?
I don't know. Again, this manufacturing will be, first and foremost, I'm not in this area. Second, there is so little information. Intriguing concept, but I don't know.
Can you hear me? Excuse me.
Yes?
Yes, yes.
So I have given this question. My name is Jerzy Jedliński, because we do look for the materials which should degrade slowly at high temperatures. And if the formation of fast-growing oxide does occur, we need to provide some kind of protective scales, and they should be operating at the high temperatures. However,
that's the point, because, sorry, your first question related us to lower temperature coatings.
Yes.
But they may not be sufficient.
Therefore, I'm asking whether the other routes of improvements are also considered in terms of finding the most slowly growing scales, or you're rather focused on application of the well-known protective scales and trying to stabilize them at high temperatures.
That's the latter one is probably more viable. Is a question of using kind of protective scales typically used at lower temperature and checking their hypotemperature potential, modifying them. But I think that's the only viable option, to extend the temperature range of currently used protective scales.
In the case of chromia, it would be a problem because they easily form a volatile species, volatile oxide. However, in the case of alumina, it might be reasonable. Okay, thank you.
And aluminum oxides melt at 2200 degrees C, roughly speaking.
Yes, that's true.
Yes, chromium would be absolutely not a good choice.
Yes. Okay. Thank you very much.
Sure. Welcome. Would you please tell us a little bit about your research and the sintering past? You only mentioned, but would you give chemical composition? Interesting. Okay.
high entropy I played was iron cobalt chromium nickel with aluminium, various concentrations of aluminium. And I tried to solve the problem. Normally when you are melting all the elements, you are going from high temperature to low. And the base structure, the composition of particular phases are stabilizing at high temperature. But what will happen when we try to come from low temperature to high, not crossing the melting point? This was my idea, and I have sintered such powders in several temperatures, starting from, I don't remember, 130 degrees higher. At 1000 degrees, I got perfect high entropy alloy, normally alloy. My procedure was that I have mixed the powders of superalloys. I have chosen the temperature a little bit of the melting point of the lowest one, so aluminum in this case, and I have sintered it for some 24 hours, and then I have increased the temperature for sintering. After several days, everything was sintered.
Thank you.
The process was limited by the student.
Yes, it was purely digital. And repeated that with copper, with zinc, with touch. That's all.
And the thinking is done in under vacuum conditions, or it is in
In capsules,
It was done in vacuum conditions, but sometimes some technical reasons, I have no such permit to operate in vacuum, so I use the capsule and some argon.
Okay, if there are no further questions, thank you for attending. Thank you for your listening.